Hi, welcome back. I'm Owen Lockwood, and today I'll be talking about the 2017 Nature paper, Hardware-Efficient Variational Quantum Eigensolver for Small Molecules and Quantum Magnets. This was put out by a team here at IBM. So in this work, they talk about and present a number of methods for applying the variational quantum eigensolver to near-term quantum hardware, which is characterized by its smaller scale and the noise present on these devices. In this paper, the problem at hand is that of applying a certain Hamiltonian to your quantum wave function and figuring out what its energy is. Specifically, we're concerned with the ground state energy of some molecules. So as you can see from this formalism, this reduces to an eigenvalue problem where we're concerned with the ground state energy, which would be the smallest eigenvalue of this Hamiltonian. So we can write this in the optimization format where we want to parametrize our wave function so that we can minimize the expected value of this Hamiltonian. And this minimization will result in a ground state and the ground state energy. So if we have our parametrized wave function, we can simply take the expectation value of this Hamiltonian, and the minimum of this will be ground state energy. Now let's take a little bit of a deeper dive into what's going on here. Specifically, what does this Hamiltonian look like? This is typically presented in the second quantized form as opposed to the first quantized form. In the second quantized form, we deal with fermionic operators. So we write this as a constant, h0, plus our core integral, which is solved by existing computational packages, hpq, and then we have our fermionic operators, the creation operators indicated by a dagger on p and q, where these are the indices that we're talking about. And then we have our electron-electron repulsion integral, hpqrs. You'll sometimes see this as gpqrs, where this deals with the kinetic energy of the electron and the electron-nuclear interaction, and this is the electron-electron repulsion. And then we have our creation and annihilation operators once again, but this time because it's electron-electron, we have 4 of them, so we have pqrs. So now we have to see how do we actually map this Hamiltonian to our quantum computer. Well, these are just going to be numbers that we have, so we have to figure out how do we map these operators to our computer, specifically to our standard gate-based operations. So the way in which this paper presents is called the parity mapper, and so what it does is it maps each operator using the following rule, which is somewhat similar to the Jordan-Wigner conversion that you may be familiar with. So it takes at a certain position, p, it maps this to our standard Pauli operators in the following way. We have 1/2, then we have x on that specific qubit p, we have z, and these are just, of course, our Pauli x, y, and z at p minus 1, plus I, y at that p index, followed by x, p plus 1 to however large our system is, n. And so the reason that we have to convert it, we can't just use, for example, if we want to create and annihilate things, we can't just use our x gate as we might think about flipping zeros and ones in a quantum computer, is because these fermionic operators have certain commutation and anti-commutation relationships that they have to satisfy, which our standard Pauli operators do not, so we have to map them in a certain way, and in this way we're going to choose the parity mapping. So just to give a concrete example of this, if we consider a fermionic operator here, the annihilation operator, and where p equals 1, and we're considering a 2-qubit system here, then this would map, we have 1/2, and then we have our xz plus I, y, I. And this is using Qiskit ordering, where x will be on the first qubit, z will be on the 0th qubit, y on the first, and I being the identity gate. And there's no x terms out here because this is just going to be a 2-qubit system. So now we can see how to measure all of these things. We can work with this Hamiltonian on our quantum computer, but now we have to deal with how do we represent this wave function on our quantum computer. So the way in which they do it in the paper is called hardware efficient Onsots, where Onsots just refers to this circuit structure. This is contrasted with what is called a problem-derived Onsots. So if you have these two opposing categories, you might think of the problem-derived as stemming from what we're concerned with in this molecular Hamiltonians. So if we have this ground state energy that we care about for molecular Hamiltonians, we start with that and then we think, what would be the best circuit structure for solving this problem? What's the best tools that would map to this problem? And so a lot of times you'll see things like unitary coupled cluster, which will have operations that look a lot like this, where you have several controlled operations like controlled X, and then you'll have a rotation gate, and then you'll have more controlled operations. And so this is a common sort of exponential operation that you'll see in a lot of unitary coupled cluster Onsots. However, as you can see immediately, you'll notice this trivial example right here on just 4 qubits already has 6 CNOTs. And this is extremely hard to do on near-term hardware because 2-qubit gates often have much lower fidelities and are much more susceptible to noise than 1-qubit gates. And so having this many for a single operation would mean that doing this whole thing on near-term hardware is very challenging. So this paper takes a different approach and says, let's start from our hardware and then work to what our problem is. So in this framework, we're starting with what is our exact hardware that we're working with. And so this would differ depending on what backend you're using, if you're using IBM hardware, or if you're using an entirely different system, what is the specifications of that system? In this case, we're going to be considering a topology of linear qubits, for example here, which some of the IBM systems have. So in this case, where these are the 5 qubits, we're going to represent this as our wave function as single qubit rotation gates followed by entangling gates. So rather than have this many multi-qubit gates, we're just going to have very efficient, very easy to do in high fidelity single qubit rotations like this, but then only some multi-qubit entanglement gates to generate an entangled state. So specifically, we're going to say it takes this form where we have our parametrized wave function. We're going to have an arbitrary number of layers here where we have our single qubit rotations, our Z, our X, our Z. And then we have our entanglers, and this is of course on every qubit that we're doing it on. And then we have our entanglers, uint, and then we can repeat this for however many layers we want, and then we apply it on our ground state. So you can see that this right here is one layer. This can be repeated arbitrarily many times. And this, rather than having so many CNOT gates, requires only an entangler that is hardware efficient. So specifically, this entanglement would look from this gate to this gate, from this gate to this gate, or from this qubit to this qubit to this qubit, and so on. Rather than, for example, doing an entangling operation from qubit over here to qubit over here would be very inefficient because you'd have to do it through these operations. Or you'll notice some IBM hardware has a topology sort of like a T, and we would not want to do a multi-qubit operation from this qubit to this qubit because we'd have to go through here, go through here, go through here, and uncompute those, which would be very expensive to do. So not only is the hardware efficiency concerned with minimizing the number of multi-qubit gates, but also matching the topology of the system that we're working on. And to further make this efficient, the entanglement doesn't care what entangling gate you use, it's just to generate this wave function that has entanglement in it. So the way in which we do this on IBM hardware, which they do in the paper, is by using a cross-resonant gate. So a CNOT, even though it's described on IBM hardware as being a native gate, is actually a cross-resonant gate followed by a single qubit rotation. So we can just do the cross-resonant gates, which will induce entanglement, and then we can skip that extra rotation, which would generate a CNOT. So a cross-resonance gate is not a good CNOT gate, but it works as an entanglement gate and shortens the amount of time that we have to run this for because it's more adaptable and more made for our hardware. So this is the key aspect of this hardware efficiency. So now that we have a way to work with our Hamiltonian and we have an effective description of our wave function that we're parametrizing, of course these are the parametrized examples, we can look at the optimization of this problem. Specifically, we're trying to solve this minimization problem here, but how do we actually go about solving that? What tools or techniques do we use to actually minimize this function that we have now described how to get? In the paper, they use something called SPSA, which stands for the Simultaneous Perturbation Stochastic Approximation. So this is a method of optimization that relies on a noisy approximate of the gradient. So if we have our typical gradient descent where we have our new parameters, t plus 1, where t is the time, where we take a step in the direction of the negative gradient, then we approximate this gradient using a special approach. And the reason it's special is the way it scales. So if we write it out, this gradient will be equal to whatever our function is. So this will be, our function here is this output. Our function of theta plus c, and this is going to be this delta is going to be a selection of random values that I'll discuss shortly. And then we have our format that looks very similar to other things such as finite difference or the quantum specific parameter shift rules. However, the key difference here lies with the scaling and with what this parameter is doing. So this is a vector of random either -1 or 1 values that are then scaled by c, and this is done all at once rather than parameter shift or finite difference or central difference where you go parameter by parameter to estimate the gradient. We do this all in one pass. So this scales what we say O of 1 or constant scaling, which means that no matter how many parameters you have, we only need to do 2 approximations. We need to get f of theta plus this perturbation and f of theta minus this perturbation. And this scales however many parameters we have. However, parameter shift and finite difference methods scale O of n, which means it scales linearly with however many parameters we have. So if we have 100 parameters, we're going to have to do 100 times the work as the constant scaling. And this is important to note that the scaling of our actual wave function is along the lines of the total number of parameters here is the number of qubits, 3 times the depth plus 2. And the reason there's a plus 2 here is because this very first rotation gates, we don't do the RZ because it's on the ground state. So RZ on the 0 state would do nothing, so we can just drop that gate. So that's where the plus 2 comes from. And so we can see now how to generate our Hamiltonian, how to measure our Hamiltonian on this quantum system using the parity mapping, how to represent our wave function using this hardware-efficient Onsots, and how to optimize this using our efficient SPSA method. So now that we have derived all the theoretical tools, let's actually jump into some code in Qiskit to see how we can do this on real systems. All right, now we're going to jump into some Qiskit code showing how to implement what we just discussed in Qiskit. So the first thing we have is a lot of imports. A lot of these are very familiar imports. We need to import our transpolation, our quantum circuit, our parameters, our quantum instance. These are very standard Qiskit tools. However, you'll notice a lot of them come from something called Qiskit Nature. And this is a module for Qiskit that contains a lot of these tools that do the natural problems for us. So molecules obviously are a nature problem. So all the tools for doing these molecular Hamiltonians lie within Qiskit Nature, which you can install separately. So the first thing we have is simply a class that containerizes our molecule, so the information regarding which molecule we're going to be using. In the drivers and problems, which are both very related, we specify that we're dealing with an electronic structured problem as opposed to there's vibrational structures or protein problems. We're specifying that we're concerned with an electronic structure problem. And you'll notice that all of these specify that we're operating in the second quantization, which is something we discussed earlier. That's how we represent our Hamiltonian. We import converters so we can map these fermionic operators to our qubits. We import transforms so we can work with our electronic Hamiltonian and reduce the problem size. And we import our parity mapper. Then we have our algorithm imports, we have SPSA already implemented for us, we have VQE, the routine, implemented for us, and we have our NumPy solver. So this will be our base case or our true case that we're comparing our VQE results against. So then we load our account, and we have to specify a backend here because we're going to be looking at specifically optimizing this setup for a given backend. In this case, I just chose this example. There's a number of other IBM hardware that you could equivalently choose. So now let's take a look and compare what our naive implementation of a hardware efficient Onsots and our aware versions would look like. So in this naive version, we're going to say our entanglers are basically just controlled knots. And that seems okay. We see that controlled X is in fact a basis gate for the IBM hardware. However, we discussed that we really want the cross-resonance gate, and that's what we're going to be doing in the hardware efficient Onsots aware function. So first we have this naive implementation, which is very similar. And so we just specify that we have our quantum circuit that we're generating based off of however many qubits we have. We specified a number of parameters as was outlined by that scaling, number of qubits times 3 times the depth plus 2. And then we have our 2 parameters here. Remember, there's no RZ because it's on the 0 state. And then we have our entangling and then our single qubit rotations. Then we have our more aware version, which is the exact same. However, this entangling section is slightly different. We have to specify that we're only doing this cross-resonance gate, which is this RZX rotation by pi over 2, and then we have to actually build this on our hardware. So we're going to simulate this, but for the sake of truth, we're actually building this as if it were on hardware. So here we imported our calibration builder, so we're sort of going inside the transpiler and doing this by hand by saying we really do in fact want this cross-resonance gate, and that's all we want. And so then we just put this in place in our circuit. Then we can make a comparison. So for a simple, in this case, hydrogen would be, H2 would be 2 qubits. For a depth 1 circuit, if we compare the pulse schedules, we can see a notable difference. Here is the naive approach. You can see our CR gates here with an additional single qubit rotation that I mentioned on the whiteboard. And if we do our aware, we can see that this is gone and we just have this cross resonance. What this results in is you can see the time up here on the top of each of these diagrams. You can see that this results in a 33% reduction effectively in the amount of time that a single pass takes, which means the faster your circuit is, the less time there is for the environment and the world to create noise in your circuit. So this makes it more resilient to noise because it's faster. So then we specify our converters that we're going to be using for all of these molecules, which are the parity mapping, and we can do a 2 qubit reduction, which just enables us to exploit the symmetry in the problem. We compare against the NumPy solver, and we're going to go through all 3 molecules presented in the paper, H2, LIH, and BH2, but the code is going to be very similar at each step. So for all cases, we have our SPSA optimizer. We're going to do a noiseless, well, we still have shot noise, but there's no actual depolarizing or decoherence noise. And then we're going to create our VQE based on this circuit. We're going to increment over the bond lengths from a specified 0.1 angstroms to 4. And then at each step, we're going to want to do the same thing for every molecule, basically. And that specify our molecule, so we're saying that our 2 hydrogens are in the same X and Y coordinates. They're just a difference of whatever our bond length is. We're specifying our driver, so we put in our molecule, we put in our basis, and here you have a number of choices. A very common choice, and the one that's used in this paper, is STO3G, which stands for Slater type orbital 3 Gaussian. So it's using 3 Gaussian approximations of the Slater type orbital, which is a minimal basis set, which means there's only one function approximating each orbital. More accurate basis functions do exist, basis sets do exist, but we stick with STO3G because it's very common for VQE. And then to generate and solve our electron core and repulsion integrals, we use Pi SCF, which is an electronic structure package that's open source that you have to install as well, but this will solve all of our Hamiltonian integrals for us. We then create our problem from this driver and use it to generate our second quantized operations that we care about. Then we'll print out some of this information that we'll look at briefly, and in both cases we want to compare the true result with our VQE calculated result. So we say we have our ground state eigensolver, we have our qubit converter, and in this case this is the true version, so we have our NumPy solver. And then we repeat this process, but we have our qubit converter with our VQE circuit instead of our NumPy. And so this will be an approximation of the ground state energy. Now we can look inside what's going on in these second quantized ops, and you'll notice something very familiar to what was on the board. We see here that we have our full fermionic operators, or this Hamiltonian that we're concerned with, where we have a constant times our creation and annihilation operators, where this is basically a hat dagger, and this is the subscript, but now it's just represented as 0 or 1. And this is our full fermionic operator Hamiltonian. We then can convert that and see what the qubit Hamiltonian is right here, and we see that it converts to a 2-qubit Hamiltonian, even though there's 4, 0, 1, 2, 3, there's 4 of the fermionic operators. Using the 2-qubit reduction and the symmetry, we can reduce this down to 2 qubits. We can then examine what's exactly going in the electronic structure problem. We see a bunch of information about what we specified in the atom, the units, the basis set, etc. But the important thing of note here is our spin orbitals. So we have 4 spin orbitals, 2 electrons, you can see here and here, and alpha and beta electrons are just fancy chemistry terms for spin up and spin down electrons. So you can only have 0 or 1. These are going to be binary because you can't have 2 spin up electrons in the same spin orbital due to the Pauli exclusion principle. And then we can see a bunch more information that, depending on the problem you're interested in, may be useful. But for now, we're just going to skip down and look at, now we see the running of this code, and this is going to be the optimization loop. And then we can see the results here. So you can see that as the bond length increases, you see a very familiar curve that looks similar to if you've seen other sort of Leonard-Jones potentials. This will be familiar, or if you've seen any other bond length variations, this follows a common pattern. And you can also note that the VQE approximations, denoted as the black dots, are very similar to the real versions. We can then repeat this process for the LiH molecule, lithium hydride, and once again we're doing the exact same steps. We have our quantum instance, we have our VQE circuit, we have 4 qubits because it's an increasing problem size, we specify our molecule, so everything else is the same. The only difference that I'm going to note here is that we now have a freeze core transform. So previously we had 2 qubits, but now we're going to have a larger number, and so we want to reduce that more using tools from our approximation toolbox. Specifically, we're going to freeze the core. What this means is that in our interaction and in our bond that we care about, we're going to assume that the inner electrons of this lithium don't really matter because they're not going to influence the bond that much. So if you consider how molecular bonds work, the 1s electrons of this lithium probably aren't going to interact that much with this bond, and that's a pretty fair assumption. We can then also remove these orbitals, specifically if we're considering we have our 1s, 2s, 2p, 3s, etc., etc. In this case, we're going to be removing the 2py and 2pz orbitals because we only care about this 2px due to the orthogonal nature of this, of the 2px to this bond that we're discussing. So we can remove those because we're assuming that they're really not going to play, those higher order orbitals aren't really going to play that much of a role in our molecule, in our bond. Everything else from then on is the exact same as the hydrogen molecule. So we can repeat this process. Here we can see a comparison. So this is the full. You'll notice this is a very large fermionic operator. You can see how the problem increases very quickly. You can see how many terms are in our Hamiltonian. So we have to go through and measure all of these different operations. And so this is, a very complex amount of measurements. But now we can see that in our unfrozen orbital, we have 12 spin orbitals, the 4 electrons. So what we're doing is we're freezing these, saying they're probably not going to interact that much in the bond. And then we're chopping these ones off, also saying they're probably not going to play that much of a role in this bond or if in the sp hybridization. So we can scroll down and we'll see the frozen version, which has now only 6 spin orbitals, which will have this one here and these 2 here. And you'll notice that this is able to get reduced to 4 qubits, as you saw in the 4-qubit Hamiltonian, because of our 2-qubit reductions. So we can repeat this optimization procedure and see that we get pretty good results, although they are not perfect or comparable to chemical accuracy, something you'll notice as well with BEH2. And the reason is that if you actually, in the noiseless version as specified in the paper, the depth required for chemical accuracy for lithium hydride is around 8, and for BEH2 it's around 28. So you can see that in this case we did depth 2, so there is some more noise. The reason we did depth 2 is simply to accelerate the simulation process. We repeat the same thing for BEH2. Exactly the same procedure here. Once again, we're freezing the core. We just remove further out orbitals because we're expanding a problem size. And we'll get a 6-qubit Hamiltonian as presented here. And you can see, once again, this has a substantial number of terms, and already very quickly you can see how the complexity of this problem increases. Once again, you'll see we'll have 14 spin orbitals here. We're going to freeze these and then chop these off to reduce it down to 8 spin orbitals, which you can see here. Since we have frozen the inner and removed the outer, we can then plot this and see pretty good results. You'll notice there is some noise that comes from both the random initialization of the parameters, the optimizer, the shot noise, and the fact that this is not enough depth to achieve chemical accuracy. This is only depth 2, whereas the paper suggests that depth above 20 is required for chemical accuracy. But you can still achieve very good results with such a low depth. Now that we've shown how to do all of this in Qiskit, let's make a brief aside showing how to do this in Qiskit runtime. So once again, we have the same set of imports, and we're going to make our hardware aware circuit here. And in this case, we're just going to be looking at a specific distance rather than plotting over the whole bond lengths. Here we're using a simulator backend. For VQE on hardware, this actually takes many hours to do and is not as fast as on the simulator because you have to do so many measurements and the optimization. It's a very surprisingly expensive calculation to do on hardware. So we're just going to be looking at software for now. But if you just changed this backend and replaced it with hardware aware backend or hardware backend here, you would be able to run this exactly on hardware. This code the exact same code would be viable for hardware. Here we can see we're just using the CHASM simulator. All of this code is copied from the VQE implementation, and we have our one difference here, which is our VQE client, which is an import from Qiskit Nature. If I scroll back up here, you can see the VQE client is imported here, and we can use this to efficiently interact with Qiskit and IBM Q runtime. So we simply specify our circuit, our optimizer, our provider, what backend we want to use, and how many shots we want to use. You can also do measurement error mitigation here. And then we just say we want to solve this problem using a very similar programmatic syntax to our traditional VQE, and then we can get the results And we can see here how for a single distance, or for a single bond length, we can see the convergence of this variational quantum eigensolver in the noiseless scenario. So now that we've outlined how you could do this on a simulator, in addition to with one line of change, how you could run this on real hardware, you should have a good understanding of the theoretical background of this paper and how to do this in Qiskit. So that's been our review of the 2017 Nature paper, Hardware-Efficient Variational Quantum Eigensolver for Small Molecules and Quantum Magnets. You can find all the code below in the description. I've been your host today, Owen Lockwood. Thanks so much for watching. See you next time.